Come on, son.
Okay.
It's okay now. Let's set it go. Is it showing there? It's because of the PowerPoint is reflecting. Is it showing? It's showing. Is it letting
I should start.
But it's not showing. This thing is still showing.
Is it still blue?
Yeah, no, it's stupid. Hmm?
Incoming call from 07.
Is it okay now? But it's something, look at this one.
Okay, good evening, class. Today we are going to start with machines, and basically there are different classes of machine or different kinds of machine. We have the mechanical machine and then the electrical machine. Basically, what we are going to do today is mainly the mechanical machine. So what is a machine? A machine is any device that is used to do work. It could be a wheelbarrow, it could be an opener, it could be a screw, it could be a screw jack, or anything. Now, such a device performs work. Such a device performs work. It performs work, and for it to perform work, an effort has to apply for a load to be moved to a particular distance. So let's talk about the terms associated with mechanical advantage. Mechanical advantage, known as, or we'll call it force ratio. Now, the mechanical advantage or force ratio is defined as the ratio of load to effort. Now, let's take, for instance, we have a screw, this device that is used to open a wine cork. Now, when you apply a force on a wine cork, when you apply an effort on a wine cork, as soon as you apply an effort on a wine cork by screwing the cork, and that is what we call effort. Now, let's say that if load is bigger than effort, that is, if load is bigger than effort, that means that the mechanical advantage is also bigger than effort, because they are in direct proportions. Now, if effort is bigger than load, that means the mechanical advantage is low, because MA, as we all know, MA, as we all know, is equal to load over effort. Mathematically, so if the effort is high, which means the mechanical advantage will be low, and if the mechanical advantage is high, the effort will be low. Now, let us talk about another thing. We have what we call the velocity ratio of a machine. Velocity ratio of a machine, which is known as VR. Now, the velocity ratio of a machine is basically inverse of the mechanical advantage. It is the ratio of effort to load. And And if velocity ratio is high, the load, which is the device that is being moved with the application of effort, is low. But if the mechanical, the load will be high. And then in a machine, the effort applied is not usually equal to 1. Reason being the fact that there are what we call frictional forces. Now, the frictional forces in the system reduces the effort applied. Total energy supplied to the system, or total work done on a system will be equal to the output work plus the frictional forces. Now, these frictional forces is what reduces the efficiency of every given machine to be less than 1 or 100%. Because in an ideal machine or in a perfect machine or a lossless machine, the efficiency of such system is 1 because there is absence of friction in the system. Now, let us look at the efficiency of a machine. I'm just trying to, summarize everything because I'm not going to go deep into it. Now, the efficiency of a machine, efficiency of a mechanical machine is equal to work output over work input times 100 over 1. Now, this is just grammar. What do you understand by the work output? What you applied in order to screw the wine cock out is what we call the work input. And work input, as I said, is usually less than 1 because of the presence of frictional forces. And then the work output is the work that is being done, the work that is done by making sure that the cock comes out. Another way you can define the work input is the work that you do in order to avert or in order to reduce the effect of frictional forces in a particular system. Now, I want us to talk about the classes of machine. There are different classes of machine. We have the class A, class B, and class C. And then what makes them to be those classes? We have class A like the lever system. Now, the lever system is a typical example is on a chair. Now, when you now apply a little effort on the lever of a chair, you see that the chair will start raising up and then start moving because of the application of effort on the handle of the lever. Now, we have the second class aspect. We have something like basically in the JAM, they don't really ask more theoretical questions. I'll go into the calculation aspect. Number 1, we are going to work on a system that is like this. We have a block and tackle system. Number 1 is a block and tackle system. We have a block and tackle system. Now, this is a block and tackle system. 1, 2, 3. Then we have a load attached to it, W. Then we have system 1, 2, 3. Hook around here. Then this load is 120 Newton. Now, the diagram represents a block and tackle pulley. system on which an effort of W Newton supports a load of 120 Newton. If the efficiency of the machine is 40%, then find the value of W. Efficiency is equal to work output over work input times 100 over 1. And then we could say that efficiency is mechanical advantage all over velocity ratio times 100 over 5 and 6. So our velocity ratio VR is equal to what? 6. And velocity ratio, since it's a ratio, it is dimensionless, so it doesn't have any unit. So efficiency of such machine, efficiency will be equal to mechanical advantage over VR times 100 over 1. We have seen the efficiency as 40. So we cross multiply, or 0 against 0. We have 4 over 10 is equal to MA over what? 6. So 10 MA is equal to 6 times 4, which is equal to 24. So MA will be equal to 24 over 10, which is equal to 2.4. Now, it is also unitless. Now, mechanical advantage, MA is equal to load over effort. So we have been given the load as 120 Newton. Then we are told to find the value of the effort, which is W there. So we now have 2.4 is equal to 120 over what? E. This is over 1. So 2.4 E is equal to 120. So E will be equal to 120 over 2.4. Mathematically, if we shift one decimal place, we have 1,200 all over 24, which is equal to 1,200 divided by 24. Will give us 50. Okay, we have another system. We have another question. Let's go to number 2 question. Number 2 question says, what effort will machine of efficiency, what effort will machine of efficiency (90% apply Newton if its effort arm is twice as load as long as its load arm. We have been given efficiency, and then we have been given velocity ratio is equal to distance moved by effort over distance moved by load. Now, from here, we are told that effort arm is twice as long as this load arm. So that means we have that effort is equal to 2L mathematically. So our effort is this. So now say 2L over what? L. So L will go against L. We are left with 2. So velocity ratio is equal to 2. Therefore, efficiency will be equal to mechanical advantage over velocity ratio times 100 over 1. Our efficiency was 90. So 90 over 100 is equal to MOA over our VR is 2. So this we cancel this. We have 18 is equal to 10 MOA. So our MOA will be equal to 18 over 10, which is 1.8. So recall that MOA is equal to load over effort. So our mechanical advantage has been given as 1.8 equal to our load from the question was 180 newtons all over effort. So our effort will be equal to 180 over 1.8, which is equal to 180 divided by 1.8. It will give us 100. So our load is equal to 100 newton. Our effort is equal to 100 newton. So that gives that. Now, the third one is a machine whose efficiency is 75. A machine whose efficiency the effort put in to the machine if it has a velocity ratio of 4. So we have a machine, and that machine maybe is a wheelbarrow, or it could be an opener, could be a clover, could be a plier. Then the efficiency of that plier is 75%, and you are using it to lift a load of this Newton. The weight of the load or the mass of the whole load is 1000 Newton. So frictional resistance. Okay, now efficiency, as we all know, is mechanical area by 4. So 100 divided by 4 will give us 25. So we have 75 is equal to 25 MOA. So MOA is 75 over 25. I think it's 3. Load to be 1000 Newton. So 3 is equal to 1000 over effort. So effort will be equal to 1000 over 3. So that gives us 1000 divided by 3. Will give us 3. This is the effort applied by that plier in order to lift this load to a particular distance. So that's it. Now, let us talk about another aspect. We have wheel and axle in a machine. Wheel and axle. Now, the velocity ratio of wheel and axle is by load. So an effort is usually applied. A force is applied for a load to move to a particular distance. And it is given as 2 pi big R over 2 pi small r. This circumference of the wheel, this represents the circumference of the axial. So 2 will cancel 2 pi will go against pi. So we have radius of the wheel over radius of the axial. So VR is equal to big R over small r. Now, from there, note that in the absence of, whenever there is no friction in the machine, the mechanical advantage. So that means, that implies that in the absence of friction, MA is equal to VR and is equal to big radius over small radius. This represents wheel, while this one represents the axial. All over radius of axial. Now we are going to solve one more question based on this. Used to a wheel and an axial is used to raise a load whose weight is 800 Newton. When if the radii of the wheel and axial are 800, the machine is. Now let us start. We are going to do small conversions here. An axial is equal to distance moved by effort over distance moved by load, and is equal to 0. Now VR is equal to, now we're going to do small conversion. You know, the unit of radius is in meters or in centimeters, but we are given millimeter here. So we say 1 meter, if 1 meter is simple stoichiometry. If 1 meter is equal to 1000 millimeter, therefore x meter will be equal to 800 millimeter. So therefore, x will be equal to 800 over 1000, which is equal to 0.8, so meters. So this represents the radius of the wheel. Then for the radius, x will be equal to, applying the same stoichiometry, 1 meter is equal to 1000, therefore 200, therefore x will be equal to 200 millimeter. So an axial will be bigger radius all over smaller radius, which is 0.8 over 0.2. Mathematically, you can shift one decimal place. So you have 8 over 2, which is 4. Mathematically, shift 1, you shift 1 down. So now we can now start doing our formula. Now it says a wheel and axle is used to ride. Now we need to calculate the efficiency of the system. Now Now, whose weight is this? So this is the load. So mechanical advantage, mechanical advantage is equal to load over effort. But load was 800 Newton and effort was 250 Newton. So MA is equal to load, which is 800 divided by 250. This will cancel this. We are having 80 divided by 25. It will give us 3.2. No unit. Now, efficiency of the machine. Efficiency of wheel and axle is equal to MOA over VR times 100 over 1. We have calculated our MOA as 3.2. So 3.2 all over our velocity ratio was 4. 4 times 100 over 1. So what divide here? Divide 100 divided by 4, 25. So therefore 25 times 3.2 will give us 80. So the efficiency of the machine is 80. So there are frictional losses in the system. So the frictional losses in the system is like 20. And that is why the efficiency of the system is 100%. Now, let us move to another question. Let us move to another question. We have a block and tackle. Block and tackle system. It says a block and tackle system is used to raise of 25 Newton through a vertical height of 30 meters. What is the efficiency? What is the efficiency of the system if the work done against friction? If the work done against friction is 1,500 joules, then G is equal to 10 meters per second squared. Now let us talk about work done. Now let us talk about work done. Total work done on the block and tackle system. Block and tackle system is equal to work done to raise work plus work done against friction. Now, work done against the load is 25 multiplied by the distance. And since the object or the machine or the load is being lifted up, or since the load is being lifted up, which means there is the presence of the influence of gravity on it. So that is why we have this 10 meters per second. So we multiply 25, which is the load, multiply by the distance, multiply by the influence of gravity, the Earth's gravitational force, which is equal to 300 times 25. It will give us 7,500 joules. Now, total work done. Total work done is equal to work done in raising this plus work done against friction, which is 7,500 joules plus 1,500 joules. So total work done on this was 1,900 joules of work done. Now, this work done is the same thing as the work output. Now, efficiency is work output done to raise the load through a vertical distance, through a vertical height of 30 meters. So it is 7,500 all over. Now, work input is the total work in the system. Two zeros will be against 2 0, 1 0 will be against 1 0. We now have 750 divided by, we have 750 divided by 9. So 750 divided by 9 will give us 83.33%. That is the efficiency of the machine. It is the efficiency of the machine. Now, let's continue. Number 6. It says a machine is used to lift a load of 10 meters. If the efficiency of the machine work is done, how much work is done? How much work is done? Now, from here, we have the height of 10 meters, a vertical height of 10 meters. And then that represents the work output. It represents the work output of a machine. Now, work output, let me start. Load is equal to 20 Newton per cent. Now, we are told to calculate work done. That is work input. Is unknown. Now, work output is equal to, which is equal to 200 joules. Now, efficiency is equal to work output over work input times 100 over 1. Now, our efficiency was 40, equal to our work output was 200 all over work input. Now we can say this is 100 over 100. This can cancel this can cancel one of these. Equal to 20 over 4, which is equal to 5%. The efficiency of the machine is 5%. Now, no, because it's work done. 5 joules. That's what we needed to calculate. We needed to calculate the work output. I've told you what I mean by work output. It is the work done when a force is applied. It's not 100% because of frictional forces. Even in the case of transformer, when you are doing electrical machines, the efficiency of transformer is never 100% because of the core losses. We have the core loss and then we have the copper loss. So also, the efficiency of a mechanical machine is not 100% because of frictions. And it is because of frictions that we now apply grease on a moving part of a machine in order. We will do one more calculation and then we move over to another topic. Because basically, the calculations I have resolved so far are the calculations I've seen in the past years. Put a call across to my boss and then he will call me and then I will give you a clearer explanation wherever and whenever it is necessary. Now, another question that says that a machine with velocity ratio of 30 moves a load of 3,000 Newton when an effort of 200 Newton is applied. Calculate the efficiency of the machine. Calculate the efficiency of the machine. Now, this is also a typical example of jam question. We have a load. Let's say this is a block. You carried a block and put it inside a wheelbarrow. And then the weight of the block in the wheelbarrow was 3,000 Newton. And then you needed to apply a force of 200 Newton to overcome the weight. And by the name of friction, which we have known. But we are now told that we should find the efficiency of such a system. Now, if we say that efficiency is mechanical advantage over velocity ratio times 100 over 1, mechanical advantage is equal to load over effort. Now, as I said, if the load is big, the effort will be small. If the load is big, the effort will be small. So which means you needed a small effort to apply or move a load a bigger load. And then since load is big, the mechanical accuracy will be big. or mechanical advantage, will be B. So we have that our load was 3,000 Newton. And then our effort was 200 Newton. Newton will cancel Newton. We are left with 15. Mind you, mechanical advantage, velocity ratio, they are dimensions. I mean that they don't have units. So we have our mechanical advantage to be 15. Then our efficiency will be equal to mechanical advantage 15 over velocity ratio, which is 30 times by 100 over 1. 0 against 0. 3 here, 1. 3 here is 5. So we have 50% efficient. 50% efficient is what the machine has. So if the machine is 50% efficient, which means there are 50% losses in the machine as well. So, which means such machine will be hot, such wheelbarrow will be having tear and wear. And in order to reduce this effect on the wheelbarrow you're using to carry such load, you need to apply grease on the moving part of the wheelbarrow so that the efficiency of the wheelbarrow will improve. Now we are going to another topic. I'm going to introduce another topic to you. So let's introduce transformer. Now, as we all know, a transformer is a static device. It doesn't move. It is there in your street. From decade to decade, from years to years, from generation to generation, the transformer you mounted either on a hedge pole or on the ground is there in your street. A transformer, as we all know, is a static device, AC supply. Now, this is a schematic diagram of a transformer. Now, a transformer consists of a core and the winding. These are the two major things inside a transformer, the core and the winding. Now, this is the core of a transformer core. It could be a ferrite, it could have a ferrite core. Ferrite core. Now, the core of a transformer could be the core type or the shell type. We have two types of core. Cores of a transformer could be shell type. It could be core type. Now, as I said, a transformer is a static device that changes the voltage of an AC supply. What I mean by AC supply is a sine function, a sinusoidal function that is like this. This is an AC supply. Now, once the AC supply comes from the transmission system, it comes from the transmission system, which is like either 33 kV line or 330 kV line. It comes here. It energizes the coil. The coil of the transformer is this, or we call it the winding of the transformer. It energizes the coil, and then as it energizes the coil, it produces what we call flux, which is directly proportional to the current. Now, as you are increasing the current in the system, because this is a sinusoidal function, what could cause an increase in current in the system could be frequency dip. A frequency of the system could rise or fall. And in such a case, there will be what we call instability in the power system. or there will be what we call loss of synchronism in the power system. I'm not going deep into it. Now, what I'm trying to tell you is that current and flux are in direct proportion in the case of transformer. Now, the current that comes in here energizes the wire and then produces a flux. Now, this flux produces here will link with the secondary winding, the generator, could be your fan or anything, which is the load. And then a transformer is an inductive load itself, which means it has a lagging current. Now, when current comes in here, this is the primary current. This is the winding, or the number of turns in the primary. This is number of turns in the secondary. Now, this is the secondary current, I2, that flows through the load. Now, the primary current produces what we call the primary induced EMF. And then the primary induced EMF now link the primary current produces the primary induced EMF as well as the primary flux, which links with the coils in the secondary part of the transformer and then induce also a secondary EMF here, E2, E1. Now, there is a voltage here, V1, which is coming from the alternating source, and also there is a voltage across the load, V2. Now, we have a transformer equation, okay, or a transformer works on the principle of electromagnetic induction. I've seen it in your exam. They say, on what principle does transformer work? Transformer works on the principle of electromagnetic induction, which says that whenever there is a change in voltage, that is E, induced EMF is equal to minus N d phi over dt. Now, this represents number of turns of the transformer, while as this one represents change in flux. Now, change in flux, as we all know, produces change in current. Change in flux is as a result of the movement or motion of the rotor or the synchronous machine, that produces change in flux. And then this change in flux induces a voltage here that causes current to flow across the load in the transformer. This is induced EMF. Now it works on the principle of electromagnetic induction, where we have that E, induced EMF E, is equal to M d phi over dt. This also represents what we call mutual flux. Mutual flux between the two systems. We have the primary flux, we have the secondary flux. Now, the combination of the primary and secondary flux, when they are linked together, whenever the transformer equation is like this. Now, since we have primary voltage, primary induced EMF, and number of secondary voltage. Now, transformer equation is given as E1 over E2 equal to V1 over V2, and is equal to N1 over N2, and is equal to I2 over I1, and is equal to K. Now, this represents a ratio between primary induced EMF and secondary induced EMF, primary voltage from the alternating source and secondary voltage across the load. Number of turns in the primary and number of turns in the secondary. Then this is secondary current over primary current. And then this is K. K is a constant. K is what we call transformation ratio. Transformation of turns and current. Now, if you want transformation ratio to be high, you can increase the secondary current. Or if you want transformation ratio to be high, you can increase the number of turns. Or if you want transformation ratio to be high, you can increase the number of volts, increasing the number of turns. Because the more the number of turns, the more the current or the more the voltage, and as well as the more the flux in the system. That is it. Now, let's talk about the losses associated with transformer. As we all know that every machine has efficiency that is less than 100%. And as a result of that, transformer, being an electrical machine, also has an efficiency that is less than 100%. And one of the problems that causes transformer losses. One of the problems that causes losses in transformer is one, we have what we call the I square R losses. 2, we have the hysteresis loss. Hysteresis loss. And then we have 3, we have the magnetic or iron core losses. Now, these are the main losses we found in every given transformer. We have the copper loss, which is associated with the winding of the system. Now, from resistance of a given material is directly proportional to length and over area. Now, if you want the effect of these losses in the transformer to be reduced, the effect of I square R losses in a transformer, that is one of the ways in which you can reduce the effect of I square R losses in transformer. Now, hysteresis loss has to do with the core of the system. Now, in the system, which will reduce the effect of the hysteresis loss. Now, the air gap in the system, which reduces the effect of Lenz's law, because according to Lenz, he says that the induced EMF in the secondary part of the voltage or the current here changes as time changes. You see, it changes as time changes. So the voltage here is different from the voltage here, is different from the voltage, is different from. So whenever there is a change in either the voltage or current in the primary winding, there will also be a change in voltage here. And that change in voltage will always act in opposition to affect this change in the primary part of the winding. And in such case, you can reduce it by the application of what I have said. You need to make an opening into the system. Now, when you make an opening into the system, into the core of the transformer, you need to design it in such a way that now we have the core loss. Now, core loss, in the case of core loss, what we do is that when we are designing a transformer, we try to insulate a transformer. By insulation, it means that you cannot design a transformer with a rod or being packed together as an insulation. So that is how it is being done. Now, these are the main things you need to know about transformer at your level. That is it. Now, a transformer has 500 turns in the primary winding and 200 tons in its secondary. If the primary induced if the secondary induced EMF is 700 volts or is 150 volts, calculate the primary EMF. Now, from transformer equation, we have that solution. We have that N1 primary is 500. We have N2 secondary turn is 200. Then we have that primary voltage or primary EMF is what we are looking for. Then secondary EMF is from transformer equation. We have E1 over E2 equal to V1 over V2 equal to N1 over N2 and is equal to I2 over I1 and is equal to K. So from here we say E1 over E2 is equal to N1 over N2. So our E1 is what we are looking for. E1 N2 is equal to N1 E2. So E1 is equal to N1 E2 all over N2. So that implies we have that E2 equal to our N1 is 500 multiplied by our E2 is 150 all over our N2 is 200. So this we cancel this we cancel this. We are left with here 25. So 25 times 15 will give us the voltage in the secondary part of the transformer. So 25 times 15 will give us 375. 375 volts. Now this is voltage in the secondary. It tells you that the transformer is a step-down transformer. As we all know, when the number of turns in primary is bigger than the number of turns in secondary, that means that E1 will be bigger than E2. And that also means that I1 will be much bigger than I2. So we call this situation step-down transformer. Conversely, or on the other hand, when E2, N2, and V2 are bigger than that of the parameters of the primary, we say it is a step-up transformer. That's how the system works. Now let us talk about the as I said, the efficiency of a transformer is not 100% because of what I said, because of the losses in the system, the core loss, the copper loss, the hysteresis loss. And efficiency of a practical transformer or you can call practical transformer or transformer on load, because a transformer could be working but it is not on load. So we call that type transformer on no load. And then when a transformer is not on load, there are some characteristics which that particular transformer behaves. So its efficiency is input times 100 over 1. It could be given as power output. Power output all over power input times 100 over 1. Now, what is power output? That is power developed in a transformer at the secondary part. Power output is equal to P2 V2 cos phi 2. Input is equal to P1 V1 cos phi 1. Now, cos phi, as we all know, is power factor. Now, since transformer is an inductive load, the power, so its power factor is always lagging, so it needs to be improved in order to increase the efficiency of the system. So we can also say that efficiency will be equal to P2 V2 over P1 V1 times 100 over 1. Or, no, power output is I2, I1, so which is I2, I1. This is power output over power input times 100 over 1 gives you the efficiency of the transformer system. That is it. Now, let me get a typical example from my book. If a transformer is used to light a lamp, rated at 60 watt, 220 volts, from 440 volt AC supply. Calculate a ratio of number of turns of the primary coil to the secondary coil. Ratio of number of turns. B. Current taken from the main circuit. Current taken from the mains circuit. If the efficiency of the transformer is 95%, if the efficiency of the transformer is 95%. Now, we have been given this, that a transformer is used to light a lamp rated at this. This is power output. This, and so this is power output. But they say we should calculate the number of turns of coil in the primary to secondary. Now, power output was 60 watts. Then primary voltage was from this AC supply. Primary voltage was 440 volts. The voltage was 220 volts. Then efficiency was 95%. That is efficiency. So in this case, from transformer equation, we have that N1 over N2 equal to V2 over V1 and is equal to I2 or V1 over V2 and is 440. So we now have N1 over N2 is equal to 440 all over. Our secondary voltage was 2:1. So N1 is to N2 is equal to 2:1. This means that N1 is 2 and N2 is equal to 1. That is the ratio, 2:1. Now, the next question says we should calculate the current in the primary. That we should find the current in the primary if the efficiency of the system is 95%. Now, efficiency, as we all know, efficiency is power output over power input times 100 over 1. Our efficiency was 95. 95 over 100 is equal to power output was 60 watts. 60 watts all over power input. Input power. So we cross multiply. We say 60 times 100 is equal to 95 times input all over 6,000. These things are not working. 6,000 all over 95. Now 6,000 divided by 95. It gives us the primary power developed in the primary part of the transformer. Now, primary power, that is power input, is equal to P1 is equal to I1 V1. Now we have gotten our primary power to be 63. So 63.15 is equal to I1 times primary voltage was given to us as 440. 440. So 63.15 is equal to 440 I1. So I1 will be 63.15 divided by 440, which will give us the primary current, or the current 63.15 divided by 440 will give us, this is the primary winding, this is the secondary winding. Now this is the load. So the current that is flowing in here is 0.14 ampere. Now the power output here, the power that is developed across the node here was 60 watts. And then the voltage across here, the potential difference across here was 220 volts. And then the potential difference across the AC potential difference here was 440 volts. And then the efficiency of the whole system was 95. With this, we can say bye-bye for today. And then we'll pick it up from next time. Good evening, class.